start streaming. And I wait for YouTube to give me the stuff. Wow, what a stream! Like I know what I'm doing. Share video link. All right, I shared that. That's good. Go back here. Go in the text chat so I can see you all. All right, we're up. We're good. Cool. All right, everyone. Last book club meeting for designing distributed systems. So we've been reading this book, 2 chapters a week, designing distributed systems. It is a freely available book by, I think Microsoft, lets us have it for free, which is why I am streaming it.
What? Microsoft giving us something for free?
I know, right? Microsoft actually doing something for the world now. Yeah. So it's a good book. It's really just introduces a bunch of patterns you can use when designing distributed systems, which is really nice because as you move forward in your career and you work on different systems and different things, it would be nice to refer back to these patterns and be like, oh, what is this pattern actually solving here? What am I doing here? And then use that potentially in your system. Last week we covered the end of part 2 and the beginning of part 3. So we covered ownership election, where we talked about how systems need to figure out who's going to own a given workload or a given task, right? And we say ownership in the sense of you're responsible for either running that task or figuring out who's going to run it and make sure that it doesn't get duplicated and whatnot, right? So somebody needs to own the task. And we discussed different ways that you can kind of decide on who's going to be the owner to be able to own these tasks. So when you have multiple nodes in your system, you can't just really send traffic to all of them, and you can't really just send traffic to one of them. I mean, you can if that's your your model that you're aiming for, but you'll want to have some sort of owner who kind of oversees where tasks go and whatnot. We talked about election. So there's protocols that you can elect an owner or a master or a leader, right? All of these terms are usually used. And then how those masters, leaders, or owners are reelected if they go down. And then we talked a bit about etcd, which is a distributed key value store. And we talked about if you didn't have some sort of protocol to do ownership election, like Raft or Paxos, you can use etcd, which is a distributed key value store, to do a distributed locking, right? So we talked a bit about that. Then we moved off of part 2 and into part 3. So part 3 covers batch computational patterns. So when you batch a workload, you take this massive workload and you cut it up into different batches and you operate on them, right? And you do work on them. If you think batching, you might think of a batch of cookies, right? And it's kind of like that. If you think about it, you have a big wad of dough and you cut out a small part of that dough to use as your batch for cookies. Same idea in computing. You have a big wad of data and you go through that data in batches. And we talked about one of the patterns you can use when you're doing batch processing, which is a work queue. A work queue is just like the queue data structure. Work comes in and it goes out, and then you can do different things with that work queue. And that's what we talked about. We'll move into the last 2 chapters today. I mean, there's technically 3 chapters, but I don't count chapter 13 because it's just 2 paragraphs of, what to think about next. So we'll cover today chapter 11, which is event-driven batch processing. So we're building more on that batch computational patterns. And chapter 12, which is coordinated batch processing. These chapters are actually really light, so I don't expect us to have a bunch to say about them. But let's just get into it. Anyone have any questions on chapter 11, event-driven batch processing?
Nope.
Sweet. Yeah, I figured this one was pretty straightforward. One thing I did want to kind of call out and note is that like this sort of event-based batch processing is pretty cool because we've talked a little bit about like event-driven systems, I believe up here. Yeah, with functions as a service, we talked about like event-based functions as a service models, and you can still have this sort of event-based architecture when you're doing batch processing, which is really nice, where like different events trigger the start of your batch processing. And the author makes a pretty cool like note here in this second paragraph where he says when you have all of these event driven systems kind of like working together where one like an event comes in, it fires off like a workflow it fires off like a batch process. That batch process finishes, it triggers an event that fires off another batch process, and so on and so forth. You can almost think about your different batch processes and your different events as a beautiful acyclic graph. And we use the term acyclic here, meaning like no cycles. That's the only, if you're hearing that term for the first time, acyclic just means there's no cycles, right? The graph traverses, in a way with no cycles. But when you build all these different little batch processes together and you tie them up together, you have what we call like a workflow, right? Where the work is moving through your system, going from batch process to batch process, triggering event after event, and it's a huge workflow. Cool. The author basically just lays out like 5 or so patterns of event-driven processing, and I'm really just gonna talk about these very briefly. So you have the first one is the copier pattern. So you have
Hey Matt,
yeah, go for
hey
it.
Matt, could you share the screen?
Oh man, I totally forgot. When I started my stream, I thought I shared my screen and I didn't. There we
Okay,
go.
thank
Sorry.
you.
I'm so bad. You know what it is? I'm looking at my screen where the stream is running and I'm seeing my own screen. And I'm like, of course, everybody sees my screen, right? And I also didn't post the YouTube link for y'all in this chat, so I'm just bad. You should fire me. It's okay. just get rid of me. Sorry. Yeah, I didn't really cover anything. I just talked about this paragraph up here where he like talks about workflows and acyclic graphs. Cool. So there's different patterns of event-driven processing that the author wants us to be aware of. The first one he introduces is called the copier pattern, where you have this is like a workflow combining multiple ones. But you have the copier pattern where you have a work queue, right? A queue of work, and it hits this copier logic that can be an application, whatever it is, that's sitting there, and it determines that this work needs to be copied and sent to 2 or more newer work queues. And the example that the author gives us is imagine you need to like transcode different video. Is it transcode? Is that what he said? Render, transcode? I don't know. I'm not in the video space. I don't know the terminology there. But he says imagine you need to like work with different video formats and you need to transcode it into like 1080p or 4K or 720p or whatever. You would receive the videos in your work queue and you'd copy them and send them to different work queues to do the different processing on them. So the copier pattern is really good when you have these distinct, when you need to take the work and perform different operations on it. So you can copy that. Any questions there? Really simple. We're going to probably run through these, but I'll stop for questions on each one. Sweet. Then the author goes into a different pattern called filter, and you'll actually start to see that these patterns feel very similar to like different programming methods. Maybe if you're from JavaScript, which I think most of us here are, you might have heard of like a filter method on like arrays and stuff where you can filter things out. You also probably heard of like reduce and map, right? And all of those things. You'll start to see how these patterns really like mirror what you can do with arrays. And if you think about it, a work queue, is really just a giant array, right? So just try to make those connections. It'll help you like keep these patterns in your mind. But the author talks about the filter pattern, where now you have this unit of work coming through your system, and you want to either do more work on that work, or you want to like drop it or ignore it, right? Think of this almost like a firewall for your work in a sense, where you have work coming through your system, and maybe you only want to process every, even number video, or every even number thing, or every work that is on Ubuntu and not on Fedora, or whatever, all the purple things and not the blue things, right? Like if you want to do some sort of filtering on the work that you have, the filter pattern is really good to do that, where you just basically have some criteria. If it matches the criteria, it continues to do more work later. If not, it just drops it and it's done. So the filter pattern. I don't think there's any questions on this one. This one's pretty straightforward. Cool. Then the author expands on the filter pattern and talks about the splitter pattern. The filter pattern is really nice because you can filter out, what you want to do and what you don't want to do. But sometimes you don't want to just drop that work that didn't match your filter like on the floor. You don't want to just like drop it. You want to send it somewhere else. So that's where you get the splitter pattern. You get different, you get work coming into your system, and then you can split it based on where it needs to go. Now you might be thinking like, hey Matt, what's the difference between this and copy? Well, copy will send a copy of the work to all of the queues, behind it, where the splitter will be selective, right? So in the example the author uses here, he talks about like different types of orders coming in, like a text order, an email order, or whatever. And then the splitter sends all text orders to one place and all email orders to another, right? For a notification system. So that would be a good use case for splitter. Any questions on splitter? It's probably too big. There we go. Sweet. If anything comes up, just stop me. Then the author goes into the sharder pattern, where it's similar to the splitter, but it breaks up the work into different shards, right? So we know, since we read this book, that you shard your data when you can't, usually when your data is too large to fit on like one system, you'll shard it, meaning you'll chop the data up into different pieces. So that way you can like work on the data in different shards and different pieces across multiple systems. Same thing here with this batch processing pattern. You'll shard up your work so that way you can spread the compute time of that work across different workflows, across different queues. And that way you increase your reliability and you also increase your throughput, right? You also get a nice little benefit here that if you shard up your work, if you deploy a new version of your code that maybe breaks things, it'll only break it on that one shard if you do like a rolling deployment. And that gives you really nice confidence because instead of having a code change break the entire pipeline, it might break one or two shards, and that's just a fraction of outage, right? Like that's just a partial outage. So you can see how these patterns are building up with one another. Sharding is really important once you get like a large amount of data in your systems, right? Like there's no one system in the entire world that can handle all the data ever. That's why we shard it across multiple systems. And same thing here with these work queues. You can't just throw everything into one giant work queue because you'll overwhelm the work queue. You'll flood it, right? You'll back it up. You'll want to shard things at some point. Any questions on the sharding side? And the author gives us this like graphic here, where he's like, orders that are even go to this queue, orders that are odd go to another queue. Sweet. The last one is the merger pattern. So the merger pattern is basically like a combination of a couple different patterns in reverse almost. It's basically like the copier pattern in reverse is what the author kind of tells us. So you take all of these different work queues and you merge them back into a single queue. I think the author, I don't know if he compares this to Reduce yet. I don't think he does. I don't remember if he compared this one to Reduce. like the reduce method where you take like, many items and you reduce it down to one. But you can kind of think of it like that as well, where you merge these different work queues into one queue. And that's really useful when you have like work going through your system, but it needs to converge to one point before it can proceed. Cool. Then the author gives us like a fictional example of implementing like new user signups, and he just goes through like, here's how you would think about doing new user signups. You can like shard it based on different things, and then after you shard it, you can copy it, one going to the welcome email, one going to the notification email, and blah blah blah. And he just shows how you can build up these different patterns together to implement like a user signup flow. Cool. I'll pause for questions there. Any questions so far? I feel like these chapters are like pretty straightforward. Sweet. Okay. The author ends this chapter with what we call like PubSub, or publisher subscriber. So PubSub is kind of like a type of message queues, or a type of work queues, or a type of queues that you can use in your batch processing. And it just stands for publisher subscriber. So if you ever hear someone say like, oh, use a PubSub, use a PubSub API. If you're from the Southern United States, specifically the Southeast United States, you might have heard PubSub as like a Publix sandwich, a Publix supermarket sandwich. That's not the PubSub we're talking about. When I used to say that when I was in Florida, people were like, you want a PubSub? Like, what? You want to go to Publix and get a chicken sandwich? But no, it's not that one. It's publisher subscriber. So it allows you to publish messages to a queue, or sometimes we call them topics. And it allows you to subscribe to those topics or queues and pull messages off of them. Okay? So just be familiar with these terminologies, because you'll probably hear people say topic a lot, because that's the term that Kafka uses, which is a very popular PubSub implementation. They use what we call topics. So you might hear people say like, oh yeah, I'll just do PubSub and I'll create 2 topics and I'll pull things up. Like, you might hear people talk like that. This is what they're referring to. They're just talking about a message queue, right? Like just a queuing system. So don't let like the terminology get you confused, right? And maybe not confused so much, but don't let the terminology kind of like turn you off of the conversation. But yeah, so basically this whole PubSub idea is that you can have one or more publishers publish the messages to that queue, and one or more subscribers pulling messages off that queue. Okay. And there's many different PubSub implementations. Every major cloud has them. Maybe some of you are familiar with Amazon SQS, Simple Queue Service. That's a very popular one. And then Kafka is a hugely popular one as well. And that's an open source one. Cool. And then the author ends the chapter like deploying Kafka, but I'm not really going to go over this because it's just him like showing commands. Any questions at all on this chapter? Or on like batch processing patterns in general?
Not this chapter, but he does mention the reduce pattern in chapter 12. Right at
Oh,
the start.
perfect. Okay. Yeah. I knew like you mentioned, I just forgot where. Is there anywhere that you can think of in life where this like PubSub, this work queue, batch processing patterns like can be used? Is there anything you can give an example of that you'd be like, oh, I wonder if that's a PubSub or a batch process?
Yeah, I have used it before, the PubSub. There's a middleware for robotics, called robotic operating system. They basically work with PubSub. So like for a joint and all that, they publish topics based on what you need. You can subscribe to it.
Nice.
Yeah, this pattern is super common with SCADA applications, so like industrial automation, because SCADA is like supervisory. I can't remember the full acronym, but basically it's like you subscribe to events, like so you get alerts from like different machines in the field and stuff. It's super common there.
Yeah, agreed. even restaurant orders, right? Like online orders come in and it's waiting for, it's subscribed to some sort of queue, and then an online order comes in and it publishes a new order to that queue, and then the subscriber says, "Oh, I got a new order. Let me ring the bell." Right, like Uber Eats or whatever, similar. Yeah, there's a lot of cool like things you can use message queues for, and they're actually really, really popular in like system design and high scale systems. So keep in mind, right? See where in your application you might need a message queue, right? Or some sort of like event driven batch processing. Cool. I mean, they have their own problems. They're not like perfect, but it's pretty nice sometimes to have these. Cool. We'll move into chapter 12, which is the final chapter like of content, because 13 is just like a goodbye chapter. And the author talks about coordinated batch processing here. And basically, the idea here is that all of these patterns that we've been talking about, all of these batch processing patterns and these work queue patterns, let's talk about doing all of them concurrently, right? So I'm not going to say in parallel technically, but I'll say concurrently, even though it might be parallel depending on if multiple ones are actually executing at the same exact time. But I'll use the term concurrently, but just in case. You don't have to just have a work queue on one system, right? You can have many work queues spread across many systems, and you can divide your work up into so many different ways and perform the work in parallel or concurrently, right? And that helps you speed up execution time. That helps you increase throughput, right? There's really a lot of nice reasons why you would want to do things concurrently. And when you do things concurrently, you do introduce some problems. And that's kind of what the author is getting into here. He says, hey, it's really nice that you can use these patterns that we saw to break up your work and distribute it onto multiple nodes to be run concurrently, right? That's fantastic. However, when you do that, you need to now join all that work back together before you move on to the next stage. Otherwise, you'll be working on incomplete data, right? Like imagine if I gave us all like we all had one phone book, right? And it was our responsibility to find all pizza places in that phone book. So I ripped the phone book into what do we have, like 4 people here? Yeah, I ripped the phone book into 4 different pieces, and I gave each one of us a piece of the phone book, and I say, hey, can you go find the pizza places in that phone book? If I want to get a total number of pizza places, or if I want to get a total, all of the pizza places, I have to wait for all 4 of us to finish. I couldn't just get the results from 2 of us and then keep going. I have to wait, right? I have to wait for all of that results to finish. So I have to wait for them. I have to join, right? Those are some of the terms that you'll hear when we talk about like concurrency. So you'll break up your work and then you have to join it back down so that you have the complete data set before you can move forward. Sometimes you'll hear this pattern called as like, a barrier. So that way nothing can proceed until all of the parallel work has finished and been joined back, right? So it's a barrier. Although I never really heard this term used in the field. So I don't know how popular that term is, but I've heard join a lot, right? So take that for what you will. Cool. So the author gives us a nice little graphic about this. You have all of these parallel work queues. They're doing their work. Once they finish, they join up at this place, this logic, and that join has to happen before more work can happen with that work. Trying to think if there's anything else I want to talk about with this. I don't think so. Cool, yeah. I'll open up for questions. Any questions on like parallelizing your work and then joining it back down? If this terminology is like new or confusing to you because you haven't done like concurrent programming before, I really, really encourage you to like go try some concurrent programming, right? Like go use Go or Rust or whatever. Hell, go even use JavaScript with promises and like do like promise dot all or something, I think is the primitive there, and see how that stuff works. Cool. I'll move up to reduce. So we know that if we're going to parallelize our work, right, if we're going to run work concurrently, we're going to have to join it back down if we want to guarantee that we have the entire data set before moving on, right? We also know that when we parallelize work, or if we shard it, right, if we shard our work and we perform it across multiple work queues, that's similar to like a programming language's map call, right? So JavaScript has a map function that you can use on like different on arrays and stuff, where you can like run a function on each element of the array, right? So that's similar to like breaking up your array and doing something on each element, which is great. However, if you then want to combine all of that stuff back down into one like value, for example, for the pizza place example, if I wanted to just know the total number of pizza places in the phone book, I'll have to reduce all of those different works that you've all done, right? Let's say I got 10 places, you got 20, someone else got 30, and someone else got, 10 again. I don't even know what numbers I said now, but I think that's 70, right? Yeah, 50. Yeah. So I would want the total number of pizza places to be 70, right? So I have to reduce those 4 different numbers that I got down to a single number. I have to reduce all that parallel work that I did back down to a single piece of data. And this is different than joining, because joining says, give me all the data before I proceed. Reduce is saying, give me all the data and I'm going to summarize it. I'm going to reduce it down into one piece of data. Okay, so if you're confused by join and reduce, that's the difference. Cool. In reduce, I think I want to show you the output. Yeah, I want to show you this example. So expanding on my pizza example of the phone book, the author says, imagine you want to count the number of words in a book, right? And you divvied up the work, like you get pages, you get all the pages that end in 1, someone gets all the pages that ends in 2, and so on and so forth. And then eventually everyone's going to have the number of words kind of looking like a hash map, right? So like the person that finished this one counted 50 A words, 17 the words, 2 cat words, 1 airplane word, and so on and so forth. And another person got 30 A words, 25 the words, 4 dog words, 2 airplane words, blah, 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 blah. If you're going to reduce this down, you don't have to wait for everybody to finish counting before you start your reduce process. That's what the author's trying to say here. And I really wanted to emphasize this point because a lot of people are like, oh, if you're reducing, you have to wait for everybody to be done before you can start reducing. No, you don't, right? I only need to wait for at least 2 of my parallelized work queues to be done before I can start reducing, which is great because if you think about it, if you count 50 pizza places and I count 30 pizza places, well, that's a total of 80 pizza places so far. And then if somebody else finishes and they count another 15 pizza places, well, now they have 95 pizza places. So as the data comes in, I can keep reducing it. And then once all the data is done, I have my final reduction and it's my single data. So I really, really wanted to drive that point home. Any questions on that or any sort of like anything unclear there that y'all want to chat about? No, Matt, you're awesome. We're going to miss you, buddy. Don't mind me. I'm just being silly.
Yeah, I have a question. So the difference between reduce and join, you have to wait, and reduce, you don't have to wait.
Exactly. The purpose of join is to wait for all of the work units to be done before proceeding. The purpose of reduce is to take all of the output of all of those work units and to compute some finalized single value. So you still have to wait for all of them to proceed, you still have to wait for all of them to finish, but you can get started on your reduction phase before everything is finished.
Okay. Makes sense.
Yep. Cool. The author goes into he gives us like 2 more examples of how reduce can be used. So the first one was counting, right? Like being able to count something. The other one is sum. So imagine you wanted to count well, I guess count and sum are really kind of the same thing, but it's slightly different when we each gives a slightly different example. But he says, imagine you want to sum up the entire population of the United States of America. You can shard that down per state, but if you do it, per state, then you might need to that might be too much for one person to count everybody in the state. So then you want to shard it down by, town or by county or whatever, right? Is that what he says? Oh, he says you might want to shard it by town first, but that might be too much. So then you want to shard it by county as well, right? So that is an example of you have this complex work that you need to do, right? Count the number of people in the United States. And in order to do that, you're going to shard up your work into different shards. But that first level of sharding isn't enough. So you need a second level of sharding on top of that. And the point the author's trying to make here is that no matter how many levels of sharding you do on the data set, the reduce can still work because it doesn't care about that. It's still going to reduce things correctly. And he just gives an example, like say, you had Seattle with 4 million and Northampton with 25K. Reduce will still see that as, 4 million and 25,000. And then so on and so forth. As that keeps happening, you'll eventually reduce it down to the entire population of the United States. But yeah, the point the author was trying to make in this example was that no matter how much you shard your data down, reduce still is going to give you that same single result back. Any questions on that? All right. And then the last example of reduction or reducing is a histogram. The author's example is imagine you want to get a histogram of the family size in the United States. Whereas the number of families that have 0 to 10 children or whatever, and get that as a percentage. The author says, even though you're working with something like percentages, you can still use math to have the reduction continuously execute even while work's being done. So the big point that the author's trying to make here is that even if you have a problem that might seem difficult to reduce, with some ingenuity or some math, you can probably reduce it if you think about it a little bit more. Yeah. I mean, I'll be honest with you, I didn't really follow this one exactly because he's you can take the population, divide it, and do this. And I was like, okay, great. I get what you're trying to say. Math. Right? You're trying to use math here. I understand. But that's all the... Sorry,
I skipped that too.
Yeah.
As soon as he started describing calculations, I was like, yep, okay.
Cool. Yeah. I was like, I get what you're trying to say. You're trying to let me know that you can still continue to do the work without waiting for everybody. You just use some math to do it. I get it. No problem. See, these sentences, math. Great. Good job. Cool. And then the author ends the chapter with a little hands-on image tagging and processing pipeline, where he's imagine you have a bunch of URLs to different images and you want it to blur the license plates out of those images. You can have different work queues, one to identify where the license plates are, one to blur the license plates, one to process the image, and he just kind of goes over that. That's really all he says there. I'm not gonna go over that one too much. But yeah, and that is coordinated batch processing. So using multiple work queues to operate on your work in parallel, right? Concurrently. Cool. Any questions on these 2 chapters? Chapter 10 chapter 11 or chapter 12?
Seemed pretty straightforward to me.
Yeah, it's pretty
Yeah.
pretty straightforward. Cool. Just to give a quick recap to whoever wants to watch this video in the future. Chapter 11, we talked about event-driven batch processing, where different events trigger these different batch processes, and the author covered 5 different patterns that you can use in this event-driven processing. You can use the copier pattern, where work comes in and it gets copied to 2 or more different work queues. The filter pattern, where you take work and you filter out what work do you actually want to continue working on, and you drop everything else. You use a splitter pattern, which is you take the work, you look at some criteria for it, and you send some of the work this way and some of the work that way, right? You split it. The sharder pattern, where you take a lot of work, and since you have a lot of work to do, you split it up into different shards so that you can operate on that work in parallel. The merger pattern is you take a bunch of different work queues and you merge it down into one queue again. And then we talked a little bit about PubSub, publisher subscriber, where it's just a message queue. You have publishers that send messages to the queue or the topic, and subscribers that pull messages off the queue or the topic. If you ever want to look and play with message queues, check out Amazon SQS or check out Kafka. Then in chapter 12, we talked about coordinated batch processing, which is just some of the extra things you can do when you're running your work in parallel. So one thing you'll probably want to do is join. You'll want to make sure that all of the work that you did in parallel gets joined back together so that you don't miss any part of the work. Then we talked about reduce, where you work on things in parallel, but you want to reduce all of that work down to a single value, right? Maybe you want to count things, maybe you want to sum things, maybe you want to build a histogram, whatever it may be. You want to take all that work that was done in parallel and reduce it down to a single value. And that's it. That's this book. Chapter 13 is just, a couple paragraphs about what you can think about going forward. And the author basically in chapter 13 just says we've been going through transformation this whole time. There was a point in time where we had no programming languages, so we built compilers and we built programming languages, and then as those experts in the field did that, it opened up the field to all of the rest of the people, and just kept opening things up for us to make things easier and easier and easier. And now we're also in the moment of technical transformation. It's never been easier to deploy containers and blah, blah, blah. So building these distributed systems is a difficult problem, but we have a lot of tooling nowadays to help make it easier for us. That's kind of what the author is saying down here. And if we follow these patterns, we should be able to meet the demands of being reliable, being scalable, and being maintainable, right? And work on these distributed systems. And that's it. Congratulations. You've read 150-ish pages of this book. Woohoo! Give yourself a claps all around. Any last minute thoughts, questions, comments, concerns before we call this book club finished?
No concerns. It was great.
Yeah, I hope it was a good read, especially after the TCP one, which is a little bit more, technical. I hope this one was a little bit more of a easy, a fresh breather.
It was, but I also looked into more things from this book.
You did extra reading?
Not extra reading per se, a bit research. I hadn't worked in containers before, so I did some research on that.
Oh, nice. Yeah. Containers are really, really useful. I use them pretty much every day now. So yeah, I know this, the author. So the author himself was one of the creators of Kubernetes, right? So that's why all the examples in this book are very Kubernetes focused and very container focused. But he does have a point. Containers are actually really nice to deploy your software. It's much better than what we used to do in back in the day. So if you have time, I would definitely encourage all of you to, install Docker on your system, install Podman, whatever you have access to, and start playing with containers. Start spinning them up, start getting to know them, because they're not going anywhere, right? If anything, we're doing more containerized things as time goes on.
Yeah, so that was good. So I just started with.
Nice. Any other questions, comments, concerns? Cool. Yeah, I know you all are probably gonna read the Rust book next, which is nice. So definitely do that if you want to learn more about a really good programming language that's compiled and strongly typed and all that good stuff. But yeah, keep moving on. I'm gonna take a little time off of the book club stuff so I can focus on starting my new role next week. Next week. So I'm gonna do that, but I do want to get back into it and read some more books. I just don't know which one next. Maybe the Unix one. I should probably reread the Unix one. I haven't read that in 10 years, so it might be nice for me to read that again. But yeah, if you have any other book recommendations, let me know. But I think you all are gonna do the Rust book, which should take you 12 weeks if you're doing a chapter a week. So I guess maybe we'll reconvene on this. I'll keep you all posted. I do want to do another book club though, because I like these things. This is a good way to learn.
Yeah.
Yeah, sound mean.
Sweet. Yeah, I will. Okay. Any other? Oh, thank you. Sorry.
No, good luck with the start of the job.
Oh yeah,
It's always
thank you.
exciting.
It's gonna be fun. It's gonna be a good time. I'm really looking forward to getting back to work, but also being off for 1 month has been fantastic. So cool. All right. Well, I will end the stream, and if there's no, any last minute questions before I end that?
I got nothing.
Sweet. All right, I'm gonna end the stream now as soon as I find OBS. There we go.